This is a lecture about the famous mole in chemistry, and the mole plays a key role in most calculations that you'll ultimately have to do in chemistry. So it's a very, very important concept to get a good handle on. Just to give you a little bit of background about why we need something like the mole, it's because chemists often need to know how many atoms or how many molecules are in a certain sample. But seeing as the size of atoms and molecules are so small that we can't even visualize them on a microscope, how on earth are we going to know how many atoms or molecules we have in a sample? So it's virtually impossible to count atoms and molecules. Therefore, we count them by weighing. We can't weigh individual atoms and molecules, but we can weigh a group of atoms or molecules. Think for a moment if you wanted to weigh a piece of sand and all you had was a bathroom scale. You couldn't get that one piece of sand to register on the scale. But if you took a handful of sand and weighed it, it would register on your bathroom scale. And then you could count how many pieces of sand were in that handful and by a calculation determine how much each grain of sand weighed. That's kind of what chemists have done with the mole. Think of the mole kind of as that handful of sand. The mole contains enough atoms or molecules that we can get a mass and then by calculation determine how much each atom or molecule weighs. So think of the mole as a counting number, just like we have convenient units like a dozen, for it always represents 12 of something. A gross represents 144 something. Imagine you had to go into a store like Office Depot and let's say you needed 500 sheets of paper. What if there were just big stacks of individual pieces of paper and you had to count out 500 sheets? That would not be very convenient. So in the paper world, that would be a ream, which is 500 individual sheets packaged for us. Well, in the chemist world, a mole, and that convenient unit happens to be 6.02 times 10 to the 23 particles. That's a lot of atoms, but that's how many atoms or molecules we need in order to have enough to weigh out and work with. And so we'll talk in a minute about where that strange number comes from, but that is a number that you need to commit to memory. We also call that Avogadro's number. Because a mole is a counting number, we could theoretically have a mole of anything. We could have a mole of marbles, a mole of sand, a mole of shoes, a mole of cars. It just wouldn't be a very convenient unit for large things like that. So really, we think of Avogadro's number, 6.02 times 10 to the 23rd, particles of either an atom or a molecule. How much is that, by the way? 6.02 times 10 to the 23rd, that's so many of something that it's almost impossible to visualize. So imagine you had soda cans. A mole, or 6.02 times 10 to the 23rd soda cans, would be enough to cover the entire surface of the Earth and extend upwards towards space 200 miles. Unbelievable. And you can read the other two just kind of for grins. But that's a huge amount. So what does that tell you about the size of atoms and molecules? So as you'll see a little bit later, a mole of atoms or a mole of molecules can be as little as just a pinch or a sprinkle. So that tells us the atoms and molecules are so small, almost beyond comprehension. All right, so here's how we get Avogadro's number, 6.02 times 10 to the 23rd. It turns out that if you weigh out exactly 12 grams of carbon-12, and hopefully from the previous lecture you've learned what that 12 means. That's the mass of this particular isotope of carbon, which is the most common isotope of carbon. Okay, so if scientists weigh out exactly precisely 12 grams of this isotope of carbon, it turns out that in that 12 grams are precisely 6.02 times 10 to the 23rd atoms of carbon-12. And so that's where the number came from. Kind of just needed a foundation basis. Now, what do we use Avogadro's number for? We use it in large part to convert between the mass or weight of something and the number of atoms or molecules in that particular mass. So really, Avogadro's number is used as a conversion factor. The conversion factors that we'll use in chemistry are usually arranged as a ratio or an equivalency, like I've shown at the bottom of the page here. Any type of conversion factor, the numerator and denominator are considered equivalent to each other. That's what makes it a conversion factor. Okay, when you convert something, you don't want to change the value of it. You just want to put it into different units. And so it's important the top and bottom of a conversion factor are equivalent to one another. And so you'll see and need to get familiar with using Avogadro's number as a conversion factor between the number of atoms or molecules and the mass. We'll start simple here. Let's say that a scientist has determined they have 2 moles of lithium, or they want 2 moles of lithium, and they want to know how many atoms that represents. Okay, so I want you to start visualizing kind of a concept map here, where if we had moles in the middle, and let's say we want to convert to particles. And what do I mean by a particle? I could mean atoms. I could mean molecules. Okay, so if we want to convert to a particle, we would use Avogadro's number, which is 6.02 times 10 to the 23rd, right here. So the key is you put the given information in the upper left, and then in ratio form, you multiply by that your conversion factor, which tells us that there are 6.02 times 10 to the 23rd atoms in 1 mole. Now this conversion factor is the same for every substance you want to convert from moles to atoms or molecules. When you have it arranged this way, you see that the original units cancel out and that the units of your answer will be atoms. Okay, so this ends up being just a simple multiplication. If we started with atoms as our given information, we would have to flip the ratio, okay, so that units atoms would be in the denominator so that they can cancel out. So you really need to include your units in these calculations and make sure they cancel out on the diagonal. And in this case, because 6.02 times 10 to the 23rd is on top, and then on the bottom in the conversion factor, this ends up being a division problem, okay? And that means we have 1 mole of carbon. So here's a little memory trick to remember. When your given or starting information is in moles, it will always be a multiplication problem. If the given information is in any unit other than moles, in this case atoms, it will be a division problem. Okay, so that's just kind of a cool little memory trick. Give these a try to see if you've got a handle on it, and I strongly encourage you to go ahead and actually try these. It turns out that students who watch someone else work problems may think they understand the process, and I've had that experience too. You watch something, yeah, that makes sense, I can do that, that's easy. But it's an entirely different story when you try to do it on your own. You discover little errors that you didn't realize you might make. So please put the video on pause and try to do these yourself, and you can check your answers on the next page. Okay, so the first learning check problem asked how many atoms were in 0.5 moles of aluminum. So 0.5 moles is our given information. It goes in the upper left of this box grid. And since the units are moles, excuse my dogs please. So since the units are moles, then we have to make sure that when we add our conversion factor, that moles is in the denominator so that these units cancel out. That means that 6.02 times 10 to the 23rd atoms is on top. If you haven't already noticed, the number 1 always goes with mole. Okay, and any conversion factor we're going to use throughout Gen Chem, the number 1 goes in front of mole. And so this ends up being a multiplication problem. Remember that when our beginning units are mole, it is always a multiplication problem. So it's basically 0.5 times Avogadro's number. So the correct answer is 3.01 times 10 to the 23rd atoms. The second problem, the beginning units were atoms, which means that we need to flip our conversion factor so that atoms is in the denominator so that the units cancel out. Remember, the 6.02 times 10 to the 23rd always goes with atoms, and the number 1 goes with mole. And this ends up being a division problem. So it's 1.8 times 10 to the 24 divided by, because 6.02 times 10 to the 23rd is in the denominator. It needs to stay in the denominator. So the answer to the second problem is 2.99 moles, and if you were paying attention to sig figs, 1.8 only has 2 sig figs, so the answer precisely should be stated as 3.0 moles with 2 sig figs. So far we've covered how to convert between particles and moles using Avogadro's number. What if we want to convert between weight or mass and moles? And actually that's the more useful conversion for chemists, because they can't count out atoms. They really can't just look at something and decide how many moles it is. They really need to weigh things. And so it's important you know how to convert between grams, which is the SI or metric unit of mass, and moles. We will be using as a conversion factor when mass is involved what's called the molar mass, and that's basically the mass of 1 mole of a substance. The units of molar mass, it's important to remember, are grams per mole. Basically, we're telling the reader how many grams there are in 1 mole. Remember, like I said a few minutes ago, the number 1 always goes in front of mole for these conversion factors. So we're going to be using molar mass as a conversion factor. I've given you the definition of molar mass. It's the mass of 1 mole of a substance, but how do we get the molar mass? So to get molar mass, you need to look at the periodic table. And throughout this Gen Chem unit, you need an easily accessible periodic table. So if you have a hardbound textbook, you can open the back flap of it and there'll be a periodic table. It's probably more convenient for you to print one out. If you just Google printable periodic table, you'll find all sorts of convenient ones you can print out. So let's do an example. Let's say you were asked to calculate the molar mass of this substance, which is calcium phosphate. The first thing you need to be able to do is count how many of each type of atom are in there. And for this, you pay attention to the subscripts. This 3 tells us that there are 3 calcium atoms in this molecule. You've got to be really careful when you have parentheses. This 4 goes only with the oxygen, okay? Means there are 4 oxygens. Excuse me. And this 2, since there are parentheses inside of it, means that there are 2 of everything inside the parentheses. So let's do a tally. We have 3 calcium atoms, and the periodic table tells you how much each calcium atom weighs, or what the mass is of each calcium atom. I know that I'm using mass and weight interchangeably, and they really are not identical, so I apologize for that. I'm going to just use mass from now on. So 3 calcium atoms, a periodic table, if you look at the bottom of the calcium box, you'll see a number there, 40.078. That is the mass of a calcium atom. So if we multiply that by 3, we get that calcium contributes 120.234 grams. Phosphorus. How many phosphorus atoms we have? Make sure that you understand how to do this. There is a 2 outside of the parentheses, so that means there are 2 phosphorus atoms. Okay, each phosphorus atom, as you look in the periodic table at the bottom of the square for phosphorus, has a mass of 30.974 grams. Okay, so we multiply that by 2 to get the total number of grams that phosphorus contributes in this compound. Finally, this is probably the trickiest part. How many oxygen atoms are in this molecule? Well, each PO4 group has 4 oxygen atoms, but there are 2 PO4 groups, so we have a total of 8 oxygen atoms. What you can do if there are 2 subscripts right next to each other, separated by parentheses, is you multiply them by each other. 4 times 2 is 8. Okay? The molar mass of oxygen, as the periodic table tells us, is 16. We have 8 oxygen, so that's a total of 128 grams contributed by oxygen in this molecule. Then you simply add all of the masses of all of the atoms up in that compound, and you get the total molar mass. Very important skill. Make sure you understand that. Here's some to give it a try yourself. Again, as I said before, I strongly suggest putting the video on pause, going through this yourself, and making sure, getting all the kinks out now before you have a quiz or a test. Let's see how you did with the sample problems. Potassium oxide was the first one, and hopefully you have a periodic table in front of you. I want to emphasize to you that whenever you're using the molar masses for a problem, you want to make sure that you carry at least 2 digits to the right of the decimal for precision. So if you look at the periodic table, potassium has a molar mass of 39.10. There are 2 potassium in each of these compounds. And so 2 times 39.10 is 78.20. There is only 1 oxygen, okay? And so the molar mass of oxygen is 16.00 precisely. And when you add these 2 masses together, you get that the molar mass of potassium oxide is 94.20. Don't forget the units, grams per mole. Aluminum hydroxide, and there is only 1 aluminum atom. Here's the molar mass from the periodic table. Now here we have parentheses again, which means that this 3 subscript applies to everything inside the parentheses. There are 3 oxygen and there are 3 hydrogen. Using the molar masses for oxygen and hydrogen, and then adding all the masses together, we get that the molar mass of aluminum hydroxide is 78.01 grams per mole. Now that you know how to calculate molar mass, what do we use it for? Molar mass is used as a conversion factor, okay, between the mass of something and how many moles we have, okay? So this is probably the most important calculation, because a chemist will go in and get the mass or weigh out a substance, and then in order to do a chemical reaction, that chemist has got to convert the mass to moles, okay? And you'll learn why moles is so useful later for chemical reactions. It's important to realize right off the bat that if you have only 1 mole of a substance, that you can immediately know how many grams you have of that substance simply by looking at the periodic table. So that mass that you see on the periodic table for each element, it does in fact represent 1 mole of that substance. Let's look at a specific example. Aluminum is often used to make lightweight structures such as bicycle frames. How many grams of aluminum are in 3 moles of aluminum? Okay, remember I told you that 1 mole of anything is equal to the molar mass on the periodic table. So you've always got to look at the periodic table and what is the mass of 1 mole of aluminum. If you look at the periodic table, it is 26.98 grams in 1 mole of aluminum. So you need to do that because that's going to be our conversion factor for this problem. So let's go ahead and set up. We have 3 moles as our given starting information. Since moles is in the numerator in our starting information, we need to arrange our conversion factor so that moles is in the denominator so that the unit moles cancels out. Remember, the number 1 goes in front of mole all the time, which means the 26.98 grams goes in the numerator. Okay, moles now cancels out on the diagonal, and because we started with the unit moles, it is a multiplication problem, so it's simply 3 times 26.98. Okay, and so 3 times, I rounded here, 27, equals 81 grams. And what that tells us then is that 3 moles of aluminum has a mass of 81 grams. So I've drawn a kind of mole map for you a couple times while working through these problems, and here's it in a little bit easier to read format. Moles is in the middle, okay, and if we want to convert back and forth between moles and number of atoms or molecules, we will use Avogadro's number. And if we want to convert between moles of an element and grams of that substance, we use the molar mass from the periodic table. Now here's a really important point. So if you're kind of in a daze, wake yourself up and listen really carefully. What if we want to convert between grams, or the mass of a substance, and the number of particles, or the number of atoms or molecules? What do? There's no way to go directly. You must go through moles. All calculations must go through moles. So each arrow represents a calculation. Okay, so if we started with grams, the first thing we'd have to do is use molar mass as a conversion factor to get moles, and then in a second calculation, convert from moles to particles using Avogadro's number. Very important concept. Here's an entire mole map. Most students think it's very helpful to have this mole map printed out while you're first learning how to do these calculations. And of course you need to know how to follow it. Let me just give you a couple of examples. Let's say that you are, remember that particles can be atoms or molecules, okay? Anything that you can count is a particle. Let's say that you're given the number of atoms, and you're asked to determine how many grams that number of atoms is. This mole map tells you that, you follow the yellow brick road, tells you that the first thing you need to do is convert from particles to moles using Avogadro's number as a conversion factor, and then in a second calculation convert from mole to gram using the molar mass. So let's try some. How many atoms of copper are there in 35.4 grams of copper? Okay, so the first thing you want to do is pay attention to the unit. We're trying to get from we're trying to get from grams to atoms, okay? If moles is not in the question, if moles does not show up in the question, that means that's the first thing that you need to do is convert to moles. Once you're in moles, you can convert to any other unit. So calculation 1 is going to moles, and then calculation 2 is going from moles to atoms. Always start with the given information in the problem, which is 35.4 in this case. Include your units. Since they're grams, we need to have grams in the bottom in our conversion factor. Anytime you're converting, your conversion involves grams, which is mass. You need to get the molar mass from the periodic table. The molar mass for carbon is 63.5, which means there are 63.5 grams of copper in 1 mole of copper. The grams cancels out. You can either get an answer to this first calculation and then set up a separate calculation, or you can do what I call a running calculation, which just smush it all together in one calculation. It's up to you. As long as you get this answer, you're fine. So if I were to stop at this point, my units would be moles. However, this question is asking for atoms, so I need to do one more calculation. Consider at this point that here's your given information. It's got units of moles, so I want moles in the bottom so the units cancel. And I'm trying to get to atoms. The units you're trying to get to go in the numerator, And the conversion factor going from moles to atoms is Avogadro's number. Remember, the number 1 always goes in front of mole. When you complete this calculation, if I just write out the math for you, it would be 35.4 times 1 times 6.02 times 10 to the 23rd, and then anything that's in the denominator. The only thing, okay, so we have 63.5 in the denominator, and I have that 1, which I'll include just so you understand where I get all the numbers from. If you plug that into your calculator, you should get 3.4 times 10 to the 23 atoms. That's how many atoms are in 35.4 grams of copper. Here's one for you to try. If you haven't done much with grams and moles and mass conversions in high school or in previous chemistry courses, it's so important that you get a lot of practice on this. So try this one on your own. When you think you have it worked out, go to the next page, next slide, and check your answer. Alrighty, so I'm going to make a little plan first. The problem, my given information was 78.4 grams of potassium, and the problem asked for atoms. I now know that if I don't read anything about moles in the question itself, that means I need to go through moles, okay? Moles has to show up in the question, and if not, you've got to make it go through moles. So if you look back at your mole map, it tells you if you want to get from grams to atoms, atoms are a type of particle, that you must first convert to moles of potassium. And to go from anything involving mass, you need the molar mass. So the molar mass of potassium is going to be our conversion factor here. And if I look in the periodic table, I can see that the molar mass of potassium is 39.10 grams per mole. Once I have the moles of potassium, I can then go to anything, in this case atoms or particles. Anytime atoms or particles is part of the calculation, I'm going to use Avogadro's number. All right, so let me go through the calculation here. Starting with 78.4 grams, using molar mass of potassium 39.10 grams in 1 mole, making sure my units cancel on the diagonal. I'm going to do a run-on calculation. I now need to go from moles to atoms. I put the units I'm trying to get to on the top, and I have to match units on the diagonal so they cancel. Number 1 always goes in front of mole. And how many atoms are there in a mole? 6.02 times 10 to the 23rd. Make sure units cancel on the diagonal, and that gives me 78.4 times 6.02 times 10 to the 23rd. The only thing on the bottom is 39.10, and then the 1 mole. When I plug all that into my calculator, I get, and let's see, how many sig figs? I should have 3 sig figs. 1.21 times 10 to the 24th, and unit should be atoms. That is my final answer. Now it's important to do a bunch of practice on this.